Hello friends, this video on isolation of elements part 7 is brought to you by examfear.com. No more fear from exam. Let's now understand how thermodynamics helps us in the process of metallurgy. See, thermodynamics, very important equation is delta G is equal to delta H minus T delta S. In this, delta G actually will tell you if reaction is feasible or not, correct? That we come to know from delta G. If it is negative, it is feasible. Delta H is nothing but it tells you whether heat is required or heat is emitted, right? T is my temperature and S is my entropy. Right, so delta G gives free energy, delta H enthalpy, T is temperature, and delta S is entropy change. That is change in randomness of the system. Correct. But the main thing is delta G. Delta G will tell you exactly if the reaction is feasible or not, whether the reaction occurs or not. So the role of reducing agent is actually to provide large negative value of delta G. See, what I mean to say is, for example, you have iron oxide. You want to reduce to iron and oxygen. Delta G for this reaction is actually positive at some temperature T, let's suppose. At some temperature T, because these delta G depends on temperature. Correct. Now, delta G is positive, that means at that particular temperature reaction is not feasible. But if you combine this with other reaction, for example, you have this carbon plus oxygen gives carbon monoxide. Delta G is negative. In fact, very negative. Let's suppose this value is minus 100 and this value is plus 40. So if you add these two, what you get is minus 60, right? It is highly negative. So if you club these two reactions, what you get is FeO plus C is nothing but Fe plus CO. So the delta G of the next net reaction is nothing but negative value. So if you club this reaction, so this reaction is feasible. So standalone reaction 1 is not feasible, reaction 2 is feasible, and reaction 3 is also feasible. Correct. So what I'm trying to say is this reaction, this second reaction is nothing but my reducing agent. Carbon is a reducing agent, right? So this reducing agent is helping to get a negative value of delta G. Delta G for this reaction was a positive value. Please note, this is all fictitious figure, right? These are not real. These are not real figures. They are not real figures. They are just figures to explain you stuffs, right? So assuming this for the reaction 1, the delta G was positive, that means this reaction was not feasible at a given temperature, and for the second reaction was actually feasible and it had very large negative value of delta G. If you club these two reactions, the final reaction you get by clubbing these two reactions, clubbing reaction 1 and reaction 2, that has a delta G value of negative. Right? So thus I can say that the role of reducing agent here is to provide large negative delta G, and large enough such that sum of these two reactions is sum of the delta G for these two reactions is negative. This is the basic concept for thermodynamics and metallurgy. To explain this further, we have something called Epigram diagram. So let's see this Epigram diagram. So this Epigram diagram was given by H.J.T. Epigram, and this is a graphical representation of Gibbs energy. As I told, delta G is nothing but delta H minus T delta S, and also delta G is nothing but minus RT and K. There are two equations. So what this guy has done is, R is constant, right? So for different temperature, this K will depend on a particular reaction, the equilibrium constant. So at different temperature, value of delta G is found for different reaction, and he has plotted that, right? So this is a graphical representation of Gibbs energy. So if you see, the blue one is my Gibbs energy. You see, this is my Gibbs energy in kilojoule per mole, right? And it actually helps us to choose the reducing agent for the reduction of oxides. Please note, in all these reactions in this, we are talking about the oxide reduction. So if you see, copper plus oxygen becomes copper oxide. All these are my oxidation reaction. Please note, in this whole diagram will have all oxidation reaction. Right? So it consists of the plot of delta G with respect to temperature. As I told, this delta G is based on temperature, right? For a given reaction, delta G based on temperature. So changing the temperature, he has plotted delta G for a given reaction. For example, delta G for Mg plus O2 is MgO. This is the reaction. And if you see, he has plotted delta G at temperature 0 degrees Celsius, at 400 degrees Celsius, 800 degrees Celsius, 1200 degrees Celsius, and so on. Right? So, and also please note that each plot is a straight line, except in some case where there is a change of phase. For example, here if you see, the straight line has changed, right? There is a change of phase here. Similarly, here if you see, the straight line has changed. It is not straight, right? It now moves up. So, or here if you see, it is in this is the angle, and the angle changed. So such case is nothing but the change of phase, maybe from solid to liquid or liquid to gas. Okay, and similarly in the same fashion you can actually draw the diagram for halides, sulfides, etc. So the last example which we have seen, that iron plus oxygen gives FeO actually breaks into iron and oxygen, right? So this reaction actually, if you see, if you talk about the delta G for this reaction, this is the reaction. So in this reaction, iron and oxygen combines to form iron oxide. And for this, delta G is given, that is minus 450. So for this reaction, delta G will be what? Delta G will be plus 450. Correct? Kilojoule per mole. Okay. So if it is plus 50, that means the reaction is not feasible. But if you see this, if you talk about this reaction, carbon plus oxygen, this reaction, right? So for this reaction, carbon plus oxygen gives CO2. For this reaction, and I'm telling about this 450 kilojoule per mole at T is equal to 0. Correct? Obviously, as we increase the temperature, this value will come down. Similarly, carbon plus oxygen, if you see this, okay, this line, let me put in red. This line, if you see, at T is equal to 0, if you see, the value is what? Minus 350. So if you add these two, what you get is 100 kilojoule per mole. It is still positive. Still positive, that means even if you club these two reactions, the reaction won't happen at T is equal to 0. Correct? So let's see at some other temperature. Let's see at T is equal to, let's suppose, we'll take 1200. So we'll see at T is equal to 1200 degrees Celsius. So at T is equal to 1200 degrees Celsius, for the first reaction I had, this reaction, right? At 1200 this value is almost here, that is almost 270 or somewhere, yeah, 250, this plus 250 kilojoule per mole. And now let's talk about this reaction. T is equal to 1200 degrees Celsius. C2O2, the dashed red line, at T is equal to 1200. This is almost same itself, right? Minus 350, same value. Now if you add these two reactions, this is at T is equal to 0, at T is equal to 1200 degrees Celsius, almost same value. So if you add this value, this minus 350 and plus 250, what you get is minus 100 kilojoule per mole. Since this is minus, that means this reaction is feasible. So thus, even if you combine these two reactions, this reaction is not feasible at T is equal to 0, but this reaction is feasible at T is equal to 1200 degrees Celsius. Thus, this epigram diagram helps us, or Epigram diagram actually, helps us to tell you which combination is feasible and with temperature. For example, and actually there is nothing but the intersection of these two lines. For example, in this case itself, iron to iron oxide and carbon to carbon monoxide, these two lines actually intersect at this point, right? So this point is almost 450, or yeah, this is 600, 500 degrees Celsius. So at above 500 degrees Celsius, these reactions will occur. So it helps us to choose which reducing agent can be used at what temperature. Correct? So if I want to reduce my iron at almost 500 degrees Celsius, I will use this carbon. Correct? If I want to reduce again this with some other thing, again I have to find place where it is intersecting. Maybe if I want to reduce using zinc, right, then I'll have to use this temperature, because the zinc line and this iron line are intersecting here at this temperature, almost 1400 degrees Celsius. So typically you find the intersection. For example, this intersection will say that these two reactions will occur at temperature beyond this. That means aluminium will get oxidized, magnesium gets oxidized here, one of them will get oxidized actually, and aluminium get reduced, I think. So above this temperature, actually magnesium can reduce aluminium. You see, for the magnesium, this value becomes more and more negative, right? You see, magnesium is actually getting oxidized. This is 0 state and this is +2 state. Okay. So actually in this range of temperature, magnesium can reduce these oxides, aluminum oxides. See, the rule is pretty simple. At a given temperature, for example here, right? So this magnesium metal will be able to reduce any of the oxides. Aluminum oxide can reduce, it can reduce zinc oxide, it can reduce carbon dioxide, even carbon dioxide also through carbon. So this magnesium is a good reducing agent. Similarly, for example, if you see here, at this point, at this temperature, in fact, iron should be in a position to reduce carbon dioxide to carbon. But if you talk about this temperature, at this temperature, if you see, carbon should be able to reduce iron. So it's pretty simple format. You take a point, anything which is above this, so this particular metal should be able to reduce oxides of these metals. So here, for example, at this temperature, my magnesium will be able to can reduce oxides of any of these metals. So lower the element in this diagram, the greater is the stability. Correct? Of the oxide form, obviously. Because if you see, the lower you go, the more is the gas energy and the more is the tendency to form, tendency of the reaction to go on the right hand side. More spontaneous the reaction becomes. Correct? So the lower the curve is, more stable the oxide is, right? More stable the oxide is, that means this reaction will happen more easily, and since this is oxidation reaction, that means it's a more stronger reducing agent. Now we'll discuss some of the limitations of this Epigram diagram. Right? The first is, it tells whether the reaction is feasible or not, but it does not tell anything about the speed of the reaction. Speed of the reaction is something which it does not tell. Also, delta G is minus RT ln K. This is the formula used to find delta G, right? But this formula assumes that my reaction is an equilibrium, because when you use this equation or this formula is used normally in case of equilibrium, because you get this equilibrium constant, but the reaction may not be in equilibrium. So this may not be 100% correct figure. Two limitation: one is it doesn't tell anything about the speed, and also to get these values it assumes that the reaction is in equilibrium. And as I told, based on this Epigram diagram, we can actually choose a temperature for a given set of reaction. For example, I want this reaction, my FeO gives Fe plus O, and C plus O gives CO. If I want the temperature for this reaction, if you see, this is an oxidation reaction, so we'll see this reaction, oxidation reaction, this is the oxidation reaction, this is the reduction reaction, FeO gives Fe. So, but Epigram diagram always has oxidation reaction, so we'll mark the corresponding oxidation reaction for this. Now, now if you see at this point, now if you see which one is reducing agent, my carbon is getting oxidized. So carbon is the reducing agent. So here at this point, now since this line is for the Fe plus O2 is FeO reaction, that means at this point my iron will be able to reduce the carbon. But if you see, these lines meet, and at this point if you see, the carbon line comes down. At this point, carbon will be able to reduce iron oxide, and that's what we are looking for. So that means that from this intersection, any point towards right, in that temperature, carbon will reduce my iron oxide, and this temperature, if you see, is nothing but almost 500 degrees Celsius, right? So you can say that typically 500 to 900, actually this is 600, almost, yeah, 500 to 900 is the temperature we use for reduction of carbon using carbon. Correct? So this Epigram diagram also helps us to find the temperature at which a particular reducing agent can be used to reduce a particular metal oxide. So now let's take some numerical. We have to suggest a condition under which magnesium can reduce aluminium. So we have seen that the one on the lower side can reduce the upper one, oxides. That means at this temperature my magnesium should be able to reduce aluminum oxide, even at this temperature, even at this temperature, even at this temperature. After this, magnesium will be able to reduce carbon, copper, iron, but it will not be able to reduce aluminum. So only till this temperature, that means 0 degrees Celsius, to almost this is how much? This is 1300 degrees Celsius, I can say. So in this temperature range, actually magnesium can reduce alumina. Beyond that, magnesium will not be able to reduce alumina. Okay. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.